This is a self-balancing pendulum that I designed and built from scratch. The commercial lab version of this, the Quanser QUBE that many universities use in their engineering control courses, they cost about £4,500. That's about $6,000. The version I made is much cheaper, costing only about £20 in parts, and you can get them from eBay or AliExpress. This device is also known as a Furuta pendulum, after the Japanese control engineer who first proposed the design in 1992 at the Tokyo Institute of Technology. It has a motor that controls the first joint and a second joint that can spin freely on a skateboard bearing. The goal is to swing the pendulum up and balance it in its upright, unstable position. And the controller currently doing this is actually a neural network running on a $2 Arduino Nano, which is a tiny microcontroller with just 32 KB of flash storage and 2 KB of RAM. But that's a topic for another video. In this video, I'll show you how I built the physical rig, the mechanical design, the electronics, and a full cost breakdown. Here's how everything is put together. First, we take the base and place a stepper motor on it. Then we cover it with the lid. After that, we mount the arm on the motor shaft, and next we insert a bearing at the end of the arm. Finally, we insert the pendulum through the bearing. This version here was one of my first prototypes, but the current version looks like this. I know that they might look very different, but structurally they're actually very similar. My initial design for the pendulum was a fully 3D printed part, but the swinging didn't feel right, so I tried adding a 2-pence coin to act as a weight. This worked really well, and I redesigned the linkage to include a slot for the 2p coin using a press-fit design. The final design took this a step further. We embed the coin in the actual 3D printed part by adding a pause at the end of just the right layer number in the slicing software. During that brief pause, we insert the coin into the slot, press resume, and then the printer deposits the plastic over the coin, fully enclosing it within the part itself. How cool is that? I really enjoy watching that stage of the printing job. The rest of the design was straightforward. Some parts are very simple, like the lid, but others have some complex geometry, like the arm or the inside of the base. The arm features slots for 2 bearings, although I'll probably simplify it to only 1 bearing, as that seems to work well enough. It also has a slot for a sensor, which I will explain shortly, and then a channel to route the wires to that sensor board. The lid has a boss feature where the wires come out of the base, which protects the wire but also acts as a hard stop that limits the range of motion of the first joint. So while both joints are rotation joints, the first has limits between plus/minus 135 degrees, whereas the second joint can rotate freely and therefore has no lower or upper limits. Finally, the base has diagonal features on both sides which allow air to flow but also to pick the electronics inside. The back of the base has slots for the USB cable, power jack, and a rocker switch for turning the pendulum on and off. Inside, there are standoff features to hold the electronics securely in place, and also these little shelves on each wall to hold the motor bracket. The bracket holds the motor in place, which has a heatsink at the back, and then the motor bracket can be mounted inside the box with a satisfying press fit. Just like so. Oh, and I almost forgot, at the bottom there are 4 indentations where we can stick 4 of these cabinet door bumpers, so that instead of sliding around the table, the device can hold steady in place. Now let's quickly walk through the electronics. We need to somehow measure the pendulum position, so the shaft of the pendulum linkage has a small slot where a magnet sits, and I just attach it with a dab of glue. This isn't a regular magnet though. Instead of having its north and south poles on the top and bottom faces, just like a fridge magnet, instead this one is diametrically magnetized, meaning that the poles run sideways across the diameter of the disc. That magnet sits right above a tiny chip on the arm called the AS5600. This is a sensor that can measure the orientation of the magnetic field, and it does this very quickly, hundreds of times per second, and very precisely as well. It's a 12-bit sensor, which means it can distinguish 4,096 different angles within a single full rotation. To put that in perspective, the pendulum measures about 6 centimeters from the motor shaft to the center of the coin, and at that length, the coin only has to move by about 1/10 of a millimeter, which is roughly the thickness of a sheet of paper or the width of a human hair, for the sensor to register a new tick. And because the whole thing is contactless, the sensor itself adds no friction at all to the joint. The only friction we have to deal with is what's already in the bearing. We need a computer to read the sensor and command the motor. I've selected a microcontroller, which is the Arduino Nano. The Nano has just 32 kilobytes of flash storage and 2 kilobytes of RAM. Flash is where the program lives, both the C++ code and eventually the neural network waits, and it stays there even when you unplug the device. RAM is the working memory, where the intermediate values are computed every control step. 32 kilobyte and 2 kilobyte really isn't that much. A single picture taken with the camera on your phone is roughly 100 times bigger than the Nano's entire flash, and 2 kilobyte of RAM is barely enough to hold a few paragraphs of plain text. So in the next video, when we get to the stage of running a neural network on this thing, every single byte will count. Next, we need a way to move the arm, and for that, I am using a NEMA 17 stepper motor. Stepper motors are great for precise positioning because each electrical pulse rotates the shaft by a fixed known angle. That means we don't need a separate encoder on the motor itself. When we ask the motor to step by a certain amount, we just assume it has actually moved by that amount. This is what's called open loop control. The motor doesn't tell us where it is. We just trust that it followed our command. That assumption usually holds, but it can break. If the pendulum pushes back hard enough on the motor, say during an aggressive swing up, the motor can skip steps. We ask for 10, but it only does like 7, and we have no way of knowing. This is something we'll need to keep in mind later when we train the policy to control the pendulum. To actually drive the motor, the Nano needs some help. A stepper turns smoothly only if its coils are switched on and off in just the right pattern at just the right time, and that is surprisingly tricky to get right. On top of that, the coils need a lot more current than what the Nano can supply, so we use a dedicated driver chip, DRV8825, that handles both. It amplifies the current and coordinates the precise on and off pattern of the coils that make the motor turn cleanly. Finally, we need power. The whole rig runs from a 12-volt wall adapter, the kind you'd find on a router, and there's a small rocker switch on the back of the enclosure so I can turn the device on and off without unplugging it. You might also notice two little components on the board sitting right next to the motor driver, a small ceramic disc and a small black cylinder. Those are called capacitors, and you can think of them as tiny, very fast batteries glued to the power rail. The motor coils get switched on and off thousands of times per second, and each switch sends a little electrical kickback into the supply. Without the capacitors, those kicks could propagate to the rest of the electronics, making the sensor readings noisy and possibly causing the Arduino to glitch. With them, the rest of the board sees a clean, steady 12 volt. So that's really it. A sensor to read where the pendulum is, a motor to push the arm, a driver to feed the motor, a microcontroller to coordinate everything, a 12 volt supply to power the rig, and a couple of capacitors to keep that supply clean. If you add up the bill of materials, the electronics, a single bearing, the wall adapter, the motor heatsink, plus a small amount of filament for the 3D printed parts, one complete rig comes in at around 20 pounds in parts. The whole assembly is press fit, and so there are no fasteners to add to that. And that's the build. 20 pounds in parts. Compared to the 4,500 pound lab version, this is genuinely affordable for hobbyists and students. You could build over 230 of these for the cost of a single Quanser. Anyway, the whole project is open source, and you can find the links to it in the description. But the pendulum isn't much without a controller. In the next video, I'll show you the second half of this project, how I trained the neural network with reinforcement learning to balance this thing and how I shrunk it down to fit on the Arduino Nano. If that sounds interesting, please subscribe so you don't miss it. Thanks for watching, and I'll see you on the next one.